Hello students, welcome to my YouTube channel Integrated Physics Studies IPS. एथरे मु ऑलरेडी प्लस 2 सेकंड ईयर सिलेबस कंप्लीट कर सारछि एबे मु प्लस 3 सीबीसीएस ऑनलाइन क्लासेस रो वीडियोज गुडा अपलोड करिवि जदि भल लागिला ताले लाइक कर देबो एवं सब्सक्राइब कर देबो जो वीडियोज गुडा मु अपलोड करिवि तार नोटिफिकेशन पई एठी बेल आइकन को ऑल रे सेट कर देबो गोटे इंपोर्टेंट जिंस वीडियोज रो ऊपर एठी जो 3 डॉट्स देखुछो तार क्वालिटी एठी देखो बाय डिफॉल्ट 360 अछि तमे ताकू पढे मध्ये परिबो एठी एडवांस रे क्लिक करी तमे रिजोल्यूशन बढ़े परिबो प्रति वीडियोज रे मु पीडीएफ लिंक देबी ताकू एठी ड्रॉप डाउन लिस्ट रो तमे क्लिक करी डाउनलोड मध्ये करि परिबो पीडीएफ को लास्ट रे एठी जो मोर चैनल नेम अछि याकू क्लिक करी तमे एठी प्ले लिस्ट को जाई मु प्रति वीडियोज को यूनिट वाइज एज पर सिलेबस सजाई की रखिथिबी तमे सर्च करि परिबो ओके थैंक यू हेलो स्टूडेंट्स आज रो टॉपिक रे हमें नानो इलेक्ट्रोमेकानिकल सिस्टम्स माने NEMS ए विषय रे पढिबा. So from the name it suggests that these systems are a class of devices integrating the electrical and mechanical functionality on a nano scale. That is why nano electromechanical systems. And typically these NEMS integrate transistors like nano electronics with mechanical pumps, mechanical actuators and motors and form physical, biological and chemical sensors. Okay, now AFM tips, that is the atomic force microscopic tips, are the key applications of these NEMS. Okay, the fabrication of NEMS are based on the top down approach, optical electron beam lithography and thermal treatments. Okay, the NEMS technology is based on the use of the allotropes of carbon such as your diamond, then the CNT, that is the carbon nanotube, and graphene. Okay, the mechanical properties of carbon allotropes are the functional to the stability of NEMS, and metallic and semiconductor conductivities of carbon allotropes will allow them to function as the transistors. Okay, similarly the graphene and diamond have high Young's modulus of elasticity with low density, low friction and large surface area, right? The carbon nanotubes have low friction which allows practically frictionless bearings. Okay, the CNTs are used as the elements of NEMS such as nanomotors, switches and high frequency oscillators. Okay, the physical strength of CNTs and graphene allow them to meet higher stress demands. Okay, because they have high Young's modulus, right? Now the electrical properties of the carbon nanotubes and graphene allow them to be used in many electrical components of NEMS. Okay, the nano transistors have been developed from the carbon nanotubes and graphene, and metallic carbon nanotubes have also been proposed for the nano electronic interconnects since they can carry high current densities. Okay, now let us see some of the applications of NEMS, which are as follows given point wise. Number 1, nano electromechanical relay is an electrically actuated switch which is built on the nano scale using the semiconductor fabrication techniques. Then number 2, NEMS mass spectrometer is an instrument which is used for the measurement of mass of analyte particles by detecting the frequency shift which is caused by the absorption of the particles on an NEMS resonator. Okay, now let us see some of the advantages of NEMS technology, which are as follows. Number 1, miniaturization and easy to integrate. Okay, then number 2, it will have low cost in the fabrication using batch processing. Okay, then number 3, it is highly adaptable for large scale fabrication. Then it is very easy to assess. Okay, then the NEMS technology has received huge expectations in order to integrate the engineering devices with life sciences, right? However, this is highly impossible with the currently available micro scale technologies. So for example, in case of drug delivery applications, it is highly required to maintain a certain degree of concentration for the drug so that they can react accordingly to procure the desired therapeutic effect. Okay, now in this case, any upper or lower limit in the concentration would seriously affect the potential of such therapeutics. Okay, so in order to overcome such hardships, the micro dosing is being engineered using the micropumps, microsensors, and microfluid channels with other essential circuits. Okay, so this is all about the NEMS, that is the nano electromechanical systems, which I have taken from one book, but however it has given a very brief description about the NEMS. Now further I have taken the same one from another book, as you can see. So here a very important thing, the difference, basic difference between MEMS and NEMS. So you know that micro means 10 to the power minus 6 and nano means 10 to the power minus 9. So obviously the NEMS devices are comparatively having smaller dimension as compared to the MEMS devices. So we can say NEMS represent the next miniaturization step from the MEMS, that is the micro electromechanical devices, whose sizes lie in the micrometer range, that is 10 to the power minus 6 meter range for MEMS. Okay, remember that. Now in other words we can say that NEMS are the MEMS scaled to submicron dimension. Okay, so as on nanoscale surface to volume ratio is increased, therefore NEMS devices are suitable for surface based sensing application, that is for example sensors of various types. Okay, so the first very large scale integration, that is VLSI, nano electromechanical device, was developed by the IBM International Business Machines. Okay, you must have noticed this IBM word in case of computer systems. Okay, so in the year 2000 it was developed. Now this NEMS device was an array of AFM tips which can heat or sense a deformable substrate in order to function as a memory device. Okay, so the first NEMS memory was developed in the year 2007. Okay, further we know that in nature life begins from a very small teeny size bacterial object, which you can say that is the flagella. So nature is using this NEMS since life began on earth. Okay, so nanomotors are essential part of biological system, that is the flagellar motor of the bacteria. Okay, but however there exist certain difficulties in the way of developing the nanomechanics. Okay, the first and foremost is the problem of communicating with and sensing the motion of the nanoscale devices, and the other problem is that little is known about the mechanical behavior of objects which have 10% or more of their atoms on the surface. Okay, so the mechanical properties of the smallest NEMS devices are expected to be very different from those in the bulk. Okay, as we are studying from the beginning that whenever we are making a body smaller, we are going to the smaller dimension and reach the nano scale, then we see that its properties like that of your mechanical, electrical, optical, it changes. Okay, so now further it is given about the resonant frequency of vibration of the beams used in NEMS, which is given by the formula F0, which is nearly equal to h by L square into E by D to the power 1 by 2, where h is the thickness and L is the length of the beam, then E is the elastic constant of the material, D is the density of the material of the beam. Okay, now further, if we advance, let us see the materials for the active parts of NEMS. Now, the active parts of these NEMS devices are usually cantilevers or doubly clamped beams of nanometer dimensions. Right, the active masses in NEMS are in the range of femtograms, that is 10 to the power minus 15 gram, and some of the materials which are used for the making of these active parts are like silicon, then silicon carbide, that is SiC, gallium arsenide, that is GaAs, then gold, platinum, and the CNT, that is the carbon nanotubes. Now out of these, silicon carbide and gallium arsenide are the materials which are available with extremely high purity as monocrystalline layers in epitaxially grown heterostructures. Okay, and it should be noted that for the structures of same dimensions, the silicon carbide, that is the SiC, produces higher resonant frequency than the silicon or GaAs, that is gallium arsenide, and this is due to higher Young's modulus and hence higher phase velocity of the silicon carbide than that of the other two materials. Okay, now the drawback of the silicon based ultra small NEMS is that they fail to achieve the desired high quality factors, that is the Q factors, because of the dominance of surface effects such as surface oxidation and reconstruction and thermoelastic damping. Okay, so high quality factors are essential for keeping the power dissipation low, because we know that the power dissipation is inversely proportional to the quality factor, and the power dissipation in a resonant mechanical system will reduce its sensitivity to externally applied forces and increases its natural line width and increases the minimum operative power levels, and hence the dissipation must be kept as low as possible. Okay, so because of the significant advancements in growth, manipulation, and knowledge of electrical and mechanical properties of carbon nanotubes, that is the CNTs, so these materials have become the most promising building blocks for the next generation of NEMS devices. Okay, so the properties of CNTs depend on the atomic arrangement. Okay, this we have already read in case of the CNT transistors. Okay, so how they are rolled about the axis, then their diameter and the length of the tubes, so all these factors actually are responsible for the properties of CNTs, right? Now the CNTs have light weights, then they are stiff, flexible, thermally stable, and chemically inert. Okay, further, the nanowires are also another class of materials which may be used for the building of the NEMS devices due to their size and controllable properties. Okay, then come to the active mass, which is actually different from that of your total mass of the resonator. Okay, so it is only a fraction of the total resonator mass, and its value depends upon the mode of clamping and vibration of the beam or cantilever. So for example, the active mass for a beam which is clamped at both the ends and operating in the lowest frequency mode, then this active mass will be about half of the total mass of the beam. Okay, now come to the quality factor. We know that the dissipation energy is inversely proportional to the quality factor. So the mechanical quality factor for a resonator is defined by the formula Q equal to 2 times of the ratio of energy stored with the energy dissipated per circle. So high Q values means less dissipation of energy, which is the case for the nano sized cantilevers, and as a result the nano-sized cantilevers based devices will be very sensitive to the external damping, and this fact is utilized in making of the sensors. Okay, now come to the characteristics of NEMS. So the NEMS devices can have very high fundamental frequencies which may reach to microwave range, that is about 100 gigahertz, then terahertz, that is 1 terahertz means 10 to the power 12 hertz frequencies may also be reached when the MEMS devices acquire the ultimate size limit of the molecules. Okay, now these terahertz frequencies are characteristic of the molecular vibrations. Okay, and at high gigahertz frequency the displacement of the cantilevers become very small, which is around 10 to the power minus 12 to 10 to the power minus 15 meters. Okay, Now the next point, due to high mechanical quality factors, that is Q value, which is around 10 to the power 3 to 10 to the power 5 or higher values, the NEMS devices have very low energy dissipation, which you have already read. Okay, so because here the power factor PD is 1 by Q, it is inversely proportional to the quality factor. Okay, so next point, the power consumption, that is P minimum, okay, which is nearly equal to kBT omega 0 by Q, is very low, which is of the order of some picowatts. Okay, picowatt means 10 to the power minus 12 watt, or even lie in the attowatts range. Okay, attowatts means 10 to the power minus 18 watts, so it is very small quantity. Okay, here kb is the Boltzmann constant, T is the absolute temperature, omega 0 is the angular frequency. Okay, now come to the next point. Due to small force constants, they have high mechanical responsivity, that is very high force sensitivity, which is ranging into attonewton level, where 1 attonewton means 10 to the power minus 18 newton. Okay, now the NEMS devices have very low heat capacities, which reaches to far below a octocalorie, where 1 octocalorie means 10 to the power minus 24 calorie. Okay, NEMS will provide extremely high level of integration of components, which is up to 10 to the power 12 per centimeter square, and it results into reduced size and lower costs of production. Okay, the NEMS devices possess mass sensitivity at the level of individual molecules. And finally, the NEMS devices have larger efficiency levels. Okay, now let us see some of the advantages of these NEMS devices. Now, since we have seen the active mass which is involved in NEMS are of the order of femtograms, that is 10 to the power minus 15 gram. So the resonant frequencies which are extremely sensitive to slightly change in the mass. Okay, so whenever there is a slight change in the mass, the resonant frequency will be very sensitive and it can detect it, so it will play like a sensor. Okay, the mass sensitivity will reach to the level of individual molecules here. Okay, and the resonant frequency f0 can be affected by the absorption of a small number of atoms on the surface, and this forms the basis for use of NEMS as very high sensitivity of your sensors. Okay, then next point, the damping or friction will be very small for nano sized beams or cantilevers which are used in the NEMS, and these devices are very sensitive to external damping. Now lastly, the nano-sized beams dissipate very little amount of energy over their vibrational cycles. Okay, so these are some of the advantages of NEMS. Now along with it, there are also some of the disadvantages or drawbacks which are causing the negative impacts. Okay, so besides many positive effects, there are also some serious concerns about the development of NEMS technology, which might have some adverse effects on the environmental conditions as well as on the socio-economical issues. Okay, so some of these points are like NEMS technology involves the use of non-biodegradable materials. So ultimately it will create pollution. Okay, because these materials will never degrade. Then next point, it lead to material toxicity. Okay, so the materials will be poisonous, okay, ultimately, and it will be harmful to the living organisms. Then the NEMS devices are difficult to handle as they are very small in size and are composed of both mechanical and electronic components. Okay, so handling of these nano sized mechanical components specially presents a very great difficulty. Okay, then there are maybe some unanticipated consequences which might not be taken care of. Okay, and lastly, since NEMS devices are highly efficient, so ultimately it may lead to job losses, that means unemployment. Okay, so due to increased manufacturing efficiency and because of the increased use of nano robots etc in the manufacturing processes, it will create unemployment. Many people will lose their job. Okay, now let us see what are the challenges in the development of NEMS. So in the first point, the size of the devices compared to their embedding circuitry, then extreme surface to volume ratios, then unconventional characteristic range of operation, then the NEMS involve the measurements of very small displacements. Hence, there is need of developing ultra sensitive, very high bandwidth displacement transducers. Okay, then in the next point, high degree control of surface quality and adsorbents is needed. Here, adsorbents or the process of adsorption means it is actually addition of ions, molecules or atoms of the gases, liquids or solutes, and combine them into a thin film of surface. Okay, so due to the unprecedented mass sensitivity, extreme cleanliness conditions which are required to be maintained during fabrication of NEMS. Okay, then extreme mass sensitivity also results in existence of large phase noise for the NEMS resonators. Okay, then new approaches of efficient actuation at the nanoscale must be developed. And lastly, precise, robust, and reproducible new approaches to the surface and bulk nano machining are required. Okay, now let us see the process of fabrication of these NEMS. So fabrication techniques such as optical lithography, e-beam lithography, and X-ray lithography, which are actually used for the semiconductor devices, are not suitable for your fabrication of NEMS due to one or other reason. So actually NEMS fabrication uses the technology which is known as the nano imprint lithography. Okay, so for the development of NEMS, the nano imprint lithography is the most promising technique. Okay, and it is a type of lithographic technique where no radiation is used for the modification of the surface of the resist. Rather, the patterns are transferred onto the surface of the resist by physically deforming the resist shape with a mold which is containing the nanostructure pattern to be transferred. Okay, and here a resist means it is a thermoplastic polymer which is used as a coating material on a substrate that softens on heating, whereas the mold is a relatively harder material that can be a metal, insulator or semiconductor, and is fabricated by using conventional lithography. Okay, so let us try to understand this fabrication process as shown in the figure. Okay, so you can see in the first figure here, this is the substrate, the lower one, then above it there is the resist. Okay, and on the upper side we have the imprint press mold and the mold containing pattern. Okay, now we know that the material of the resist will be softened upon heating and the substrate is a harder material. Okay, now our task is to transfer the pattern from the mold to the resist. Okay, and for this purpose we have to press the mold upon the resist. Okay, so it will create a contrast pattern in the resist as shown in the second figure. Okay, so upon pressing you can see after removal of the mold, this is the contrast pattern created in the resist, right? Now after the mold is lifted off, then etching will be done to remove the remaining resist material in the compressed regions. Okay, and during molding process the resist is heated and become softer than the mold, right? Now the resist is heated above its glass transition temperature, which allows it to flow and conform to the mold pattern. Okay, and this technique is capable of producing patterns with 10 nanometer of resolution. So this is the final conformation of the pattern. Okay, which is the pattern transfer in the resist. Okay, so the advantages of this nano imprint lithography is that its high production rate and low cost. Hence, due to these characteristics, this technology is suitable for large scale development of NEMS based devices. Okay, now finally the applications of NEMS. So here the nano electromechanical systems, that is the NEMS, are very useful for the surface based sensing mechanisms, and the NEMS technology actually promised to revolutionize measurements of extremely small displacements, extremely weak forces, particularly at the molecular level. Okay, NEMS may provide ultra low power electromechanical signal processing and computation. Okay, but however, to utilize full potential of NEMS, high quality transducers must be developed such that its internally generated noise has a magnitude which should be comparable or smaller than the thermomechanical fluctuations. Okay, the high Q devices, that is the devices having high quality factor, will have low thermomechanical noise and hence less random mechanical fluctuations, and also they will have less energy consumptions. Okay, so due to their exceptional characteristics as stated above, the NEMS have the following applications, okay, which are given in the pointwise manner. So in the first point, NEMS can be used as force sensors, chemical sensors for detecting chemical substances in the air, and also will be used as a biological sensor. Now their key application is in the AFM tips, that is the atomic force microscopic tips. Higher sensitivity of NEMS will lead to smaller and more efficient sensors to detect stresses, vibrations and forces at the atomic level, etc. Then in the next point, the nano nozzles in the inkjet printers. So here also the NEMS can be utilized. Now in the next point, NEMS accelerometers, which measures the tilting of and orientation of mobile phones. Okay, and these micrometer sized accelerometers are already in use for the activating airbags in the cars. Okay, now moving on to the next point, the NEMS can be used as miniature robots such as nano robots, self assembly robots, etc. Then as ultra high frequency resonators, then in the field of medicine as pressure sensor in order to measure the blood pressure. Okay, NEMS may lead to the development of MRFM, that is the magnetic resonance force microscopy. Then they can be used as thermal actuators, which are able to deliver large force with large displacement to the overall device for small amount of thermal expansion in one part. And finally, in the field of biotechnology, they can be used in lithographic methods to assemble inorganic and metallic materials to layered devices. Okay, so this is all about the nano electromechanical systems, that is NEMS. Okay, at the end, I advise you to go through the PDF completely, which I have taken from two books. And initially, from the first book that I have taken, it has given about NEMS in a brief manner, and in the second book, it has given about the NEMS in a detailed way. Okay, so I advise you to read from both the books and combine it and make your note accordingly. Okay.
Thank you.